Hey guys, this is CHEM 1412 Final Exam Review Part 2. Alright, so 70 questions total. You have 110 minutes. You're given most of the needed equations and all of the necessary constants that you could possibly want for this. Okay, so from chapter 13, 14, and 15, so that's all of equilibrium stuff, acids and bases and buffers. There are about 23 questions. There are all the topics that they are over, so pause the video, write them down, whatever you want to do. Right here, chapter 16, thermodynamics, and chapter 17, electrochemistry. It's 15 questions total, and then from chapter 22, about 2 questions. Okay, so for equilibrium, what you need to know or remember is that equilibrium is occurring when the rate of the forward reaction is equal to the rate of the reverse reaction. So when that happens, the reaction appears not to be changing anymore. So it looks like the reaction has stopped, but really the reactants are just being produced as quickly as the products are being produced. So you don't see a change anymore. The equilibrium expression only contains gases and aqueous substances. And I also want to put in there that whenever you make a K, you have to put raise them to the coefficients. So if our reaction is this, remember the coefficients are exponents. K does not change unless the temperature changes, so K is a constant. It's going to stay the same no matter what unless the temperature changes. This is the only thing that can change K. When Q is less than K, the reaction is going to go towards the products. When Q is equal to K, reaction is at equilibrium. And when Q is bigger than K, the reaction shifts towards the reactants. Okay, so you either need to have that memorized or understand that if Q is less than K, that means Q needs to get bigger. And so in order for Q to get bigger, Q has the same formula as K. And so if, again, our reaction is this one up here, and this is our K, if Q is less than K, then we need A to gain so that Q can get bigger, right? Because this would be Q. It's just not necessarily at equilibrium. It's any time during the reaction. And with K right here, this is only at equilibrium. So if our Q is less than K, then we need more A. And if we need more A, then if we need more A, then the reaction has to go forward, right, to make this bigger until it equals K. And then the opposite is true. If Q is bigger than K, right, then we need Q to get smaller until it reaches K, and so we'd have to make the product smaller and the reactants bigger, and so the reaction would have to go to the left. A change in the reaction will force the reaction in the direction that undoes the change. So if we increase a product, if this goes up, the reaction has to go away from it. If a reactant goes up, the reaction has to go away from it. If we make the product go down, it's going to go towards it and produce more of it. So whatever undoes the change, that is going to be the direction that the reaction goes. And then for changes in heat, for exothermic reactions, so if this is an exothermic reaction, then the heat is a product. And so if we increase the temperature, the reaction will go away from that increase. And if it's the opposite, if heat was a reactant, if heat is a reactant, then if we increase the temperature, the reaction is going to go towards the products. All right. So which depiction to the right shows the equilibrium relationship below? Assume all of the volumes are the same. So if we look at this first one right here, right, we have 2 circles as a product and 1 star as the reactant. So we're going to pretend that all of these are going to be in the equilibrium expression, and so K would be equal to 2 circles, so 2 squared divided by 2, which would equal 2. And so we would have to figure out which one of these is at equilibrium by calculating Q. And so for A, we've got 1, 2, 3, 4. So that would be 4 squared divided by 1, 2, 3, 4, 5, 6 divided by 6. And so that's 16 divided by 6. That's definitely not 2. All right, so for B, we've got 1, 2, 3, 4. So again, it's 4 squared divided by 1, 2, 3, 4, 5, 6, 7, 8 divided by 8. So that's 16 divided by 8, which does equal 2. And so B would be at equilibrium. And we could just double check C real quick. So I've got 1, 2, 3, 4, 5. So that would be 5 squared divided by 1, 2, 3, 4, 5, 6, 7, 8. And so that's 25 divided by 8, and that is definitely not 2. So again, that reinforces the answer is B. All right, equilibrium expression and finding K, Kp, changes in volume, temperature, and Q. All right, so what is the equilibrium expression for Kc for the reaction that's shown right here? And so if we wanted to write K for this, it would be Kc is equal to the concentration of CO2 cubed, because you can't forget the coefficient. Now, this would not be included in our K because it's a liquid, and liquids are not included, only gases and aqueous substances. Okay, and then that would be divided by the concentration of carbon monoxide cubed. And again, we would not include iron 3 oxide because it's a solid. All right, so on number 1, it says if the value for K is 13.4 at 25 degrees Celsius, what is the value of Kp? So for number 1, if you remember, the formula is Kp is equal to Kc times RT delta N. And delta N is the number of moles of gas products minus gas, this says gas, reactants. So it's the change in the number of gas moles. So if I look at my reactant or my product, I've got 3 moles of gas on the product side. So 3 minus, and then I have 3 moles of gas on the reactant side, minus 3. And so my delta N is equal to 0. And so I get Kp is equal to Kc RT raised to the 0. And anything raised to the 0 is 1. You can put it in your calculator. If you want to put 1,000 raised to 0, you're going to get 1. And so this turns into 1. And so Kp is equal to Kc. So that's something really that you should probably know, is that when there are the same number of gas moles on product side and reactant side, Kp is equal to Kc. All right. So then we get, if this reaction is endothermic, how would a raise in temperature affect the equilibrium? So it says it's endothermic. So if it's endothermic, that means that the heat is a reactant. So I'm going to write delta H as a reactant because the heat is going into the reaction. So if we increase the temperature, it's going to go towards the products. And if we decrease the temperature, it's going to go towards the reactants. And if the reaction were exothermic, then heat would be a product. And if heat is a product and we increase the temperature, then it's going to go back toward the reactants. If we increase over here, it's going to go back this way. Oops. So reactants. And then, of course, if we decrease the temperature, it's going to go towards the products to make more heat until it gets back up to equilibrium. All right. Number 4, if there was an increase in the concentration of carbon dioxide, how would the reaction proceed? So if carbon dioxide goes up, the reaction has to shift away from that increase. So it would go to the reactant side. And if the volume was decreased, how would the reaction proceed? So if the volume decreases, the reaction always goes to side with least moles of gas. And so since the reactant side has 3 moles of gas and the product side has 3 moles of gas, right? Then nothing is going to happen. It's no change. If the partial pressure of carbon dioxide was decreased, how would the reaction proceed? So this time, let's see if I can get rid of it. This time, if carbon dioxide is decreased, I'm going to rewrite the reaction down here. All right, so it says if the partial pressure of CO2 was decreased, so this would be going down, then the reaction has to replace what's missing to a certain degree until K is reached again. So the reaction would go towards the products. And what would the Kc be for the reaction to oh, I wrote this reaction down here completely wrong, didn't I? Okay, that should not be there. All right, so we have 2 Fe2O3 solid plus 6 CO goes to 4 iron liquids plus 6 CO2 gas. All right, so this time it says what would the Kc be for this reaction? So I'm going to rewrite the Kc for the original reaction. And we had K is equal to the concentration of CO2 cubed divided by the concentration of CO cubed. In this one we've got, and I'm going to make this Kc prime, we've got the concentration of CO2 to the 6th over the concentration of carbon monoxide to the 6th. And so you can see a lot of students, they want to say that it's doubled, that it's 2K, and it's not, because going from here to here, it is not doubled, it's squared. So we could take this and multiply it by itself, and we would end up getting Kc prime. And so that means that Kc prime is equal to Kc squared, because we've got 2 of them, it's squared. Okay. If both gases have the same concentrations at a particular time during the reaction, which direction will the reaction proceed? All right, so our K was given as 13.4, right? Oops. So K, C is equal to 13.4. And the question says, if both gases have the same concentrations at a particular time during the reaction, which direction will the reaction proceed? So Q, because it doesn't say it's at equilibrium, will be equal to the concentration of CO2 cubed divided by the concentration of carbon monoxide cubed. And if both of these have the exact same concentration, then that means that Q is equal to 1. And so if Q is equal to 1, Q is less than K, and the reaction will go towards the products until equilibrium is reached. If you want to think about it conceptually, Q needs to get bigger. It needs to get up until it becomes 13.4, and the only way to make this number bigger is to increase the product and decrease. So this has to go down, and that has to go up. Decrease the reactant. If we do that, then this number can get bigger until it reaches 13.4, and so that's why we're going to go towards the product, because the product is in the numerator of Q. All right. Finding equilibrium concentrations at a particular temperature, the following reaction takes place. If the initial partial pressure of phosphorus is equal to 1.5 and the initial partial pressure of H2 is 1.85, what is the value of the partial pressure of pH3 at equilibrium? All right, so for this one, I'm going to make a rice table because I've got initial partial pressures and I have a K, right? And I need to know an equilibrium. So that means I have a rice table that I need to make. So it's going to be RICE, reaction, initial, change, and equilibrium. So the reaction is going to be P2 plus 3H2 goes to 2pH3. And it says the initial partial pressure of phosphorus is 1.5. I'm going to write this in blue. 1.5. And hydrogen is 1.85. And we don't have any pH3. All right, now my change, which direction does this reaction have to go? Can it go towards the reactants? It can't. It can't go towards the reactants because we don't have any of this to make this over here. It has to go forward. And so if it has to go forward, then that means we're going to get 2x over here. We're going to lose 3x right here, and we're going to lose 1x right here. And these coefficients just come from the coefficients in the balanced equations. It's just from stoichiometry. All right. So we're going to end up with at equilibrium, we're going to have 2x, 1.85 minus 3x, and 1.5 minus x. Now to solve, I'm going to put this in my K, and my K would be equal to the partial pressure, this is Kp, the partial pressure of pH3 squared divided by the partial pressure of P2 times the partial pressure of H2 cubed. So I'm going to plug all of my equilibrium pressures into that. And so I've got 2x squared divided by 1.85 minus 3x cubed times 1.5 minus x, right? And that's going to be equal to 2.5 times 10, and I can't see it, my pause button is in the way, times 10 to the negative fifth. All right, so since my K is very small here, and these numbers right here are quite big, then I'm going to make these negligible and cancel them out so I don't end up with some crazy equation to solve. And I'm going to have to take 1.85 cubed. So that gives me 6.33. I'm going to rewrite all this stuff right here. So I've got 4x squared over 6.33 times 1.5 is equal to 2.5 times 10 to the negative fifth. All right, and then I'm going to go ahead and multiply these two together. And so that would be 4x cubed, or squared, divided by 9.50 is equal to 2.5 times 10 to the negative fifth. So now I'm going to multiply both sides by 9.5 to get rid of it over here. And then I will have 4x squared is equal to 2.37 times 10 to the negative fourth. Divide both sides by 4. And take the square root. And so x is equal to 7.7 times 10 to the negative third. All right. So now I need to shrink this stuff down so that we can see this. I'm going to go ahead and circle this. So we can find it quickly. All right. And we want to find the partial pressure of pH 3. And so we found x. This is x right here. And it says the partial pressure of pH 3 at equilibrium is 2 times x. So we're going to have to multiply this by 2. And so we get 0.015 atm. So that's just x, this times 2 gives us that. All right, strong acids and bases versus weak acids and bases. Remember, strong acids and bases dissociate 100%. So if you have 2 molar solution of nitric acid, you're going to get 2 molar H, and you're also going to get 2 molar nitrate. So all of this, where's my pointer? All of this turns into this. So there's essentially none of this in the solution. There's no HNO3. It's all H's and all NO3s. But whenever you have a weak acid, that's not what happens. So we have hypochlorous acid here, and only very, very little of this and very little of this is produced, and there's quite a bit of this left in the solution. The bigger the K is, the more product we make, right? So the bigger the K, the stronger the acid is. So, and I mean the stronger the weak acid is, because a strong acid doesn't have a K associated with it. And so that's the same for bases. The bigger the Kb, the more hydroxide will be produced, and so the stronger the weak base is. All right, so which depiction below shows a concentrated strong acid? So if we look at this one over here, if we look at this one, oh, that's not a very good color either. Let's see. All right, that's not working. White, okay. So if we look at this one right here, you can see that these are still together. That represents an acid, okay, because this is the proton, hydrogen ion, is connected to the conjugate base still, and so this is a weak acid. This is also a weak acid because we still have some HA or whatever that is, HX. All right, now this is a strong acid, but so is this one, because none of the conjugate bases are attached to any of the protons. But this question is kind of a tricky question because it says concentrated. And so concentrated would be D, because it's got way more of the acid, the H plus in it than B does. And so B would be considered, I guess, dilute, and D would be concentrated. All right, types of acids and bases. Rheneus produces hydrogen ions in an aqueous solution. Bases produce hydroxide when in aqueous solution. So if we look at this is hydrochloric acid, right? And it produces hydrogen in solution and chloride in solution. Sodium hydroxide produces sodium and hydroxide in solution. So these are the simplest, the first terms that were come up with for an acid base. And then as we moved through history, Bronsted-Lowry came along and said, well, more than what we suggested up here as a base, actually as a base, bases can just accept the hydrogen ion. They don't necessarily have to directly produce hydroxide like sodium hydroxide or beryllium hydroxide would. And so if we look here, HCl can donate a hydrogen to water, and water becomes hydronium down here. And so because of that, this would actually be considered a base. So water can act as a base, or really it can act as an acid too. It's called amphoterism. It can exist both as an acid or a base. All right, and then acids are electron pair acceptors, and bases are electron pair donors, not donators, donors. All right, so this is just a newer definition of an acid or a base. This is the exact same reaction down here as up here. It's just the chlorides are removed because they're really spectator ions, because this is really just H plus and Cl minus. So if you look here, this is how this right here is how this reaction is working. The lone pair of electrons on oxygen are being donated to this hydrogen. And so the hydrogen is the electron pair acceptors, and the water is the donors, and it can produce hydronium. So this is just this definition allows us to add more things into the definition of an acid or a base, some salts and things like that, that would not necessarily work this way, but does change the pH dramatically. All right, so conjugate acid-base pairs. If we look at this reaction, HI is an acid. We should all know that. It starts with an H. NH3 is a base, and it's a base because if we look at this reaction, HI can donate the H here, which makes this NH4, and it makes this iodide because it would be left alone. And so if we look at the forward reaction, we get that HI is an acid and NH3 is a base. If we look at the reverse reaction, NH4 is donating the hydrogen ion to iodide to become NH3. And so this would be the conjugate acid, and this would be the conjugate base. All right, so on number 1, identify the Bronsted-Lowry acid in the reaction. So if we look here, what has happened, and so that's why I wrote this up here, because this is kind of a weird way to write this. So I'm going to break it apart so we can see it. This is actually, oops. It's frustrating. It's actually that. And so if we look back at this is not losing an H, but this is, and so this is my acid. And I just want to remind you guys, if it's an acid, like hydrochloric acid, nitric acid, acetic acid, it's an acid. It can't ever be a base. if someone's writing it as a base, they're trying to trick you, and they really shouldn't, because chances are it's not going to act as a base. Like hydrochloric acid would never accept a hydrogen. All right, number 2, which conjugate acid-base pair is not correctly matched? So if this is an acid, then it loses a hydrogen, so its conjugate base would be chloride, and so A is correct. If this is acting as an acid, it's going to lose a hydrogen, and so it becomes hydroxide. So this one's correct. If this is acting as an acid, it's going to lose a hydrogen, and so it would become ClO4-. And if this is an acid, it's going to lose a hydrogen, and so its conjugate base is H2PO4-1-. So this one is not correct. All right. Important things to remember: the bigger the Ka, the more the acid dissociates. This means that it is stronger than an acid with a smaller Ka. It also means that it will have a lower pH than a weaker acid at the same concentration. This is because if the acid dissociates more, it makes more hydrogen or hydronium. At the same concentrations, the acid with the larger Ka will have the higher percent ionization because it makes more ions. And so here's 2 formulas. When I converted this to PDF to import it into the app that I'm using, it shifted it up. I don't know why, but whatever. So what you really need to know here is that the bigger the K, the bigger the percent ionization, and the lower the pH, as long as they're at the same concentration. And so the strongest acid in this table is going to be the one with the biggest Ka, and so that would be formic acid. Because 1.8 times 10 to the negative 4 is this, and then the next one is 1.8 times 10 to the negative 5. So remember, these exponents being negative means that it's a smaller number if the exponent is larger. Which would have the highest percent ionization? The highest percent ionization, as long as they're at the same concentration, would be formic again. And then the lowest would be hypochlorous, because it has the smallest Ka. If you have a 0.75 molar solution of acetic acid, what is the pH? So that is going to be an equilibrium problem, because all I have is initial, and in order to find the pH, I need the concentration of H at equilibrium. So that's my reaction, dissociation reaction, and I have 0.75 here, and this is a Rice table. So my change, negative x plus x plus x, this becomes x and x, 0.75 minus x, and I've got x squared divided by 0.75 minus x is equal to 1.8 times 10 to the negative 5th. And so I am going to get rid of this x, because this number is much, much bigger than this number, and so even if we found x, it probably wouldn't affect the amount we have here. And then I multiplied these two together and took the square root, so I just solved for x, and x happens to be 3.67 times 10 to the negative 3rd. And so this is also the concentration of H, right? And so then to find the pH, I'm going to take the negative log of that number, 3.67 times 10 to the negative 3rd, and that is 2.43. Okay, number 4 says the pH of a 0.1 molar solution of lactic acid is 2.43. What is the percent ionization? So percent ionization is the concentration of H, right, divided by the concentration of HA. So I am going to find the concentration of H first. Whoa, what was that? My whole page shifted weird. Okay. Concentration of H is going to be equal to 10 to the negative pH. And so that's 10 to the negative 2.43. So if I stick that in my calculator, I get 3.71 or 3.72. So 3.7 times 10 to the negative third is my concentration of H. And so then again, to find the percent ionization, I'm going to take my H and divide by the acid concentration that we started with times 100. And so percent ionization will be equal to 3.7 times 10 to the negative third divided by 0.1 times 100. And so that's going to be 3.72%. All right, and then what is the Ka for lactic acid at this temperature? So for that, I'm going to go ahead and set up a rice table real quick. Now lactic acid, I don't have the formula for that, so I'm just going to put HA because it doesn't matter. I know that my initial concentration, that's an E, it's just having issues, is 0.1. I don't have any H or any A, but I do know at equilibrium I get 3.7 times 10 to the negative third. And so that's going to be the same thing for A minus, because if I produce a hydrogen here, I also have to produce an anion here because they used to be together. So I'll get 3.7 times 10 to the negative third for my conjugate base, which means that on this side, it went up by that much. And if we produced it over here, if we make it, it has to disappear on the other side. So I'm going to take 0.1 minus 3.7 times 10 to the negative third, and I get 0.0963. And so that was just taking 0.1 minus 3.7 times 10 to the negative third. All right, and so that's 0.0963. So then to find K, it's going to be the concentration of H times the concentration of the conjugate base divided by the concentration of the acid initially, or I'm sorry, the equilibrium, and that's going to be 3.7 times 10 to the negative third times 3.7 times 10 to the negative third divided by 0.0963. And so that's going to be 1.4 times 10 to the negative 4. All right, so there's the whole screen if you need to pause it and check your stuff or whatever. There we go. All right. The following Kas listed in the table are for 0.5 molar H2CO3. What is the most prevalent species in the reaction vessel at equilibrium? All right, so our Ka1 is much, much bigger. And that's usually the case. The first Ka is usually much bigger than Ka2. And the first K is H2CO3. goes to hydrogen ion plus HCO3 minus bicarbonate. And then the second one, oops, this should be a 2. Is that. And so remember, hydrogen ions and hydronium ions are the exact same thing. So it's definitely probably not going to be this. It's most likely going to be this, because our K is so small that that means we're going to have more reactant than anything else in the solution. And since this K is bigger than this, that means that this acid is stronger, and so there's going to be more dissociation of even that acid than the second one. So if we get very little of this, then it's going to produce even less of this. So the most prevalent species is going to be the initial acid. All right, pH of a salt. Salts can either make a basic, acidic, or neutral solution. Neutral salts, the salts will produce strong acids and bases in water. Acidic salts, the salt will produce strong acids and weak bases in water. And basic salts, the salt will produce strong bases and weak acids in water. And so there's a little bit more explanation there if you need it. I'm going to do the examples. You can pause the video and try to do them on your own based on the explanations up above. All right, so AlCl3. If I look at this, that could make AlOH3 and HCl. This is a strong acid. This is a weak base. And so this is going to be an acidic salt. An explanation of that, this will stay dissociated in water, and so this is going to pull hydroxides out of the water, making excess H, and so it's going to make it acidic. Oops. Ki. We would make KOH and HI. And so this is a strong base, and this is a strong acid, and so this would be neutral. NaOH and HClO3. All right, so this is going to be a strong base and a strong acid, and so this one is going to be neutral as well. All right, buffers. Buffers are made from a weak acid and its conjugate base, or a weak base and its conjugate acid. Here's the equation. pH is equal to the pKa plus the log of the base over the acid. It's the Henderson-Hasselbalch equation. So anytime you see a buffer, you need to know that it's Henderson-Hasselbalch, and you should use this equation. Remember, the base is the conjugate base of the acid, or the acid is the conjugate acid of the base. You can't put hydroxide in here. You can't put hydronium in here. It has to be the conjugate acid or base to whatever it is you're looking at. All right, and when the concentration of the acid and the conjugate base are equal, the pH will be equal to the pKa. And so I'm just going to show you that real quick. If this is our if that's our formula, if these two things are equal, so let's say it's 2, and this is 2, 2 over 2 is 1, and the log of 1, that whole thing becomes 0, and so the pH is equal to the pKa. All right, so number 1, which of the following will create a buffer solution? For A, HClO4 is strong, and so no buffer can be made from that. For B, we have KOH and K2SO3. So this is a strong base and a salt. No buffer can be made from that either. Okay, and then the next one, C, we've got NH4Br and NH3. Now this is a weak base, and then this right here is really NH4 plus, and so that would be the conjugate acid. And so this right here is a buffer. And then part D, HCl is a strong acid, and that's a strong base, and so no buffer can be made from that either. So C is the correct answer. The next question, what is the pH of an aqueous solution of equal volumes of 0.75 formic acid and 0.4 molar sodium formate? The Ka of formic acid is 1.8 times 10 to the negative 4. All right, let's see. So I'm going to do this one in green. So the acid is 0.75, and you see how that says formic, and this is formate. Formate means that that's the conjugate base of formic acid. So the base is equal to 0.40 molar. And so that's going to be the pH is equal to the pKa plus the log of the base, the conjugate base, divided by the weak acid. All right, and so what's pKa? Well, anytime you see P in front of something, that just means to take the negative log. And so I'm going to take pH, take the negative log of 1.8 times 10 to the negative 4, and add that to the log of 0.4 divided by 0.75. And so this one right here becomes negative 0.27. And then the pKa, negative log of 1.8 times 10 to the negative 4, is 3.74. And so the pH is equal to the sum of those two, 3.74 minus 0.27, and that's 3.47. What is the pH when HCO2H and NaCO2H are equal? So when formic acid and sodium formate are the same, we have this situation, and so the pH would be equal to 3.74. It would be equal to the pKa, because this part of the equation would be equal to 0. All right, titration. So you probably should be able to recognize what is going on with the titration. And so this is a strong acid because we started a very low pH, and it's being titrated with a strong base because the equivalence point right here is at 7. All right, this one is a weak acid strong base. It has this really strange curve right here at the beginning that you don't see over here. It has a little curve right at the beginning. It has this buffer region where the weak acid is the strong base is producing the conjugate base of the weak acid. And the pH at the equivalence point is going to be greater than 7 because when this takes place, we're producing the conjugate base. And so that's all that's in solution at the equivalence point because the acid and the base are equal, and so you just have conjugate base in solution. So I'm going to show you an example of that. If we have HA, our weak acid, and we titrate that with hydroxide, then we're going to be producing water, which is neutral, right? And A minus. Now A minus is the base. It's the conjugate base of HA. And so that's why it has a greater than 7 pH. All right, and then this. All right, so sorry I got interrupted. This right here is a weak base. It has a high pH, but it's not real high, and it's being titrated with a strong acid. So it's the opposite of what's being what's happening here. We're making a conjugate acid here, and so the pH at the equivalence point is going to be less than 7. And then the polyprotic acid, so this is actually a diprotic acid, right? 2 protons, which is 2 hydrogens, hydrogen ions. There's 2 Ks here, and so that's why it has 2 equivalence points. So you'll see these little hills. You'll see more than one if it's polyprotic. If it's a triprotic acid, you'd see 3. All right, next, entropy. Woo, that should be capitalized. Entropy is the amount of chaos or disorder that a reaction has. And for the sign of delta S of a reaction, if the entropy is increasing, the sign is positive. And so like if more moles of a gas are produced, then the sign would be positive. If the entropy is decreasing, the sign is negative, less moles of a gas. Less moles of gas produced than what it started with. So substances have different standard molar entropies, and so that's just this. There's no change. It's not a reaction. It's just a standard molar entropy for a substance. The higher the temperature, the higher the entropy, the more space, the bigger the entropy, and the more bonds, the higher the entropy. So if we look here at number 1, which substance has the highest standard molar entropy at 25 degrees Celsius, I'm going to draw these for you so you can see them. And so A is CH4, it looks like this. B is C2H6, or H4. It looks like that. And then C it looks like this. So definitely C has more bonds in it, and so it's going to have a higher standard molar entropy. And what is the sign of delta S for this reaction? We have 4 moles of a gas on the reactant side, and it's going to make 2 moles of a gas. And so since we have more moles on the reactant side, the entropy is decreasing. And so that means delta S of the reaction has a negative sign. Entropy of the universe. According to the second law of thermodynamics, the entropy of the universe should always be increasing for a spontaneous reaction. So if the reaction is spontaneous, the delta S of the universe, or delta S total, should be positive. That does not mean that a spontaneous reaction has to have increasing entropy. Do not get that confused. The entropy of a reaction is only part of entropy of the universe. So if a chemical reaction happens, it's not the whole universe. All right, so don't get that confused. So let's say you have the entropy of a system is decreasing. So we have entropy, of a system is decreasing. It's negative. And the reaction is spontaneous. And so what does that have to mean? Well, we know that if it's spontaneous, then the delta S of the surroundings has to be positive. And it has to be more positive than the delta S of the system. And if the delta S of the surroundings is positive, then that means that delta H oh my goodness, is negative. So I'm going to look at this from a different perspective too, not just from the second law of thermodynamics. But if a reaction is spontaneous, then what does that say about delta G? Delta G is negative for all spontaneous reactions all the time. So if delta G is negative, we also know that delta G is equal to delta H minus T delta S, and this would be for the system, and this would be for the system, and this would be for the system. So if delta S of the system is negative, like we decided up here, right? And the reaction is spontaneous, this has to be negative. So then this right here, that part becomes positive. And if that part is positive, then this has to be negative in order to give us a negative delta G. So that also says that delta H is negative, or the reaction is exothermic. That's what a negative delta G means. All right, free energy. So for this, the amount of free energy of a reaction is the amount of energy that is available to do work. And for a spontaneous reaction, the delta G must be negative. So here's one way to find delta G. Here's another way to find delta G. There's a couple other reactions or equations, but we're just going to work with this right now. So if we have this reaction and these are the values that we have for delta G, then we want to know if it's spontaneous. I'm just going to find delta G and see if it's negative. So to do that, remember it's products minus reactants times their coefficients. So we've got two H2Os, and H2O is negative 228.6 plus 3 sulfurs, and sulfur is 0, minus, now I can do my reactants, right, because it's products minus reactants. So sulfur dioxide is negative 300.2. We've only got one of them, plus 2 H2S, and so H2S is right here. So that's going to be 2 times negative 33.6. And so this is for negative 457.2 minus negative 2 times negative 33.6 plus negative 300.2. And so I've got negative 457.2 minus negative 367.4. And I get negative 89.8. And the units are kilojoules. And so yes, this reaction would be spontaneous because we've got a negative delta G. All right, signs for a spontaneous reaction. You either need to have this table memorized or you need to understand how it works, one or the other. Okay, and it all comes from delta G is equal to delta H minus T delta S. So for instance, I'm only going to go over part of this right here. Okay, if delta H is positive and delta S is negative, then that means that this right here will be positive, and we have a positive, so we add these two together and we would get positive, and so it would never be spontaneous because we would always get a positive delta G. And in order for a reaction to be spontaneous, delta G has to be negative. All right, K and delta G, or Q and delta G. So the little knot up here means it's happening at standard states or under standard conditions. And so all gases have a partial pressure of 1, all aqueous solutions have a concentration of 1, all solids and liquids are pure, and the temperature is happening at 25 degrees Celsius. With delta G, you don't have that. And so this part of this equation is basically telling you how much delta G is deviating, changing from delta G naught. So if the reaction is spontaneous in the forward direction, and the change makes the reaction shift to products, then delta G will become more negative, more spontaneous. So if we look at this reaction, and Q is equal to 25.3, and K is equal to 7.5, okay, what does the K imply about delta G naught? And so if we have a positive K, then that means we're going to end up with a negative delta G. And so that means that this reaction is spontaneous in the forward direction. And so delta G naught would be negative. All right? And then if It says, what if the Q is larger than K, what does that say about delta G? So if we look at that, since Q is bigger than K, the reaction is going to the left. If the reaction is going to the left, then it's no longer spontaneous in the forward direction because it's going backward. And so that means that this is going to be positive because it's going backwards. And so the reverse of that reaction would be spontaneous, right? The reverse of because this is representing the forward reaction. And if it's going backwards, then it's not going in the forward reaction. So the backwards reaction is spontaneous. And if the reaction above were at equilibrium, what change could be made to decrease the delta G? And so if we want delta G to go down to make it more spontaneous, then we would have to decrease the concentration of X or increase the concentration of Y. So let me explain that. All right, so if this is our reaction right here, and if we decrease X, so X goes down, then that means the reaction is going to go forward, which means delta G is going to become more negative, and so it's going to decrease. When the delta G of the reaction is less than 0, what does that mean for K? So if delta G naught is less than 0, so it's negative, then K will be greater than 1. Because it's spontaneous, that means you're going to be making product. The reaction is product favored. And K is always the products over reactants. So if it's product favor and you're making lots of product, then this is really big and that is really small, and so you're going to always get a greater than 1 K. All right, oxidation versus reduction. Oxidation, the substance loses electrons, the oxidation number goes up. Reduction, the substance gains electrons, the oxidation number goes down. And so here's some rules for assigning oxidation numbers if you cannot remember them. I suggest that you pause the video and write them down. Otherwise, I'm just going to get started here. And so the oxidation number of manganese changes from to in this redox reaction. So I'm just going to look at permanganate here. And so it says here that oxygen is always -2 unless it's a peroxide, then it is -1. So oxygen is -2. If we have 4 oxygens, that's -8. And we have to have 1 negative left over. So that means that manganese, since there's only 1 of them, is going to be +7. Because if we take the sum of this, it equals -1. That's why this has that charge. So manganese is +7 initially. And then we have manganese dioxide. And oxygen here is -2. We've got 2 of them, so that's -4. And so manganese is going to be +4 because there is no charge here, so the sum has to be 0. If you add these 2 together, you would get 0, and so manganese goes to +4. So it's +7 to +4. All right, reducing agent versus oxidizing agent. So remember, if it has the word agent at the end of it, then that means that it's swapped. Your travel agent doesn't go on vacation with you. It only assists you in traveling. So a reducing agent is being oxidized and allowing the other substance to be reduced. And an oxidizing agent is being reduced and allowing the other substance to be oxidized. And so what makes a good reducing agent? A reducing agent gets oxidized well. A good reducing agent will have a very negative standard reduction potential. Remember, when a substance undergoes oxidation, the cell potential changes signs because the reaction is flipped. And so which of the following is the most powerful reducing agent? And a reducing agent, I would mark it out and say oxidized. So which one of these would be good at being oxidized? it would be the one that would be flipped and give you the greatest cell potential, and so that would be sodium. Because if we had to flip this one, it would be oxidized. It'd be Na goes to Na plus 1 electron, and that would give us a plus 2.71, which would give our overall cell potential a very big number. And so that's why that is the most powerful reducing agent. All right, galvanic cells will always have a positive cell potential. The anode is where oxidation occurs. It produces electrons, right? So if this is where the anode is, then it's producing electrons, and so the electrons are going to travel this way. And the negative charge has to be replenished by the anions in the salt bridge. So the negative charges will come over here, and the positive charges will go over here. And the anode has a negative charge. The cathode has a positive charge. It's where adduction occurs, and it's taking in electrons. Since the electrons are being gained over here, the positive charges has to travel down here to neutralize the negative charges that it's gaining. And so here's a couple of ways to remember that. Electrons always go from anode to cathode, A to C. It's alphabetic order. If electrons are going to the cathode, they would only be attracted to a positive charge. That's why this is positively charged. Therefore, the cathode must be positive. Also, cations are positive and move towards the cathode. Anions are negative and move towards the anode. And those are the anions and the cations from the salt bridge. All right? If the change makes the reaction shift towards the products, then the cell potential will become more favorable. If the standard cell potential is already positive, it will become more positive. If the change makes the reaction shift towards the reactants, then the standard cell potential will become less favorable. If the standard cell potential is positive, it will become less positive or even negative. All right, so if we have this reaction, okay, it says, what is the cell potential for the galvanic cell pictured on the left? So if these are the two that are happening here, this is the standard reduction potential for this, and if we leave it this way and we flip this one, if we leave this way and we flip this one, we'd end up with a negative cell potential, and that can't be right. A galvanic cell has to have a positive cell potential. So I'm going to flip this one to positive 0.76 and add 0.34 to it. And so that is going to be equal to 1.10 volts. So that is my cell potential. What is the reaction that is taking place? Remember, we flipped this one. And so if I add these two together, that cancels out. And so that would be my overall reaction. To which electrode are the electrons flowing? So we're going to be losing electrons from the zinc because they're being produced, and so electrons are going this direction. Into which electrode are the sodium ions flowing? So the sodium ions in the salt bridge have to go down here to help neutralize some of the negative charge that this cell on this side is gaining. What would you need to do to get a more negative voltage? So if we wanted a negative voltage, we would want the reaction to shift towards the reactants, and so we could increase the concentration of zinc. Or we could decrease the concentration of copper, and that would cause this to go down. All right. A current of 0.25 amps is passed through an aqueous solution of iron sulfate. For 25 minutes, what mass of iron is plated out? So as soon as I see amps, I'm going to cancel that out and put coulomb seconds because that's what it is. When I look at these two numbers that are given to me, I have to start with one of them. I'm always going to start with the number that doesn't have any units in the denominator, which is 25 minutes because we've got seconds here in the denominator for the amps. But before I can actually use that, I've got to get seconds. So I've got minutes right now, so there's 1 minute is 60 seconds. And then I can use 0.25 coulombs per second. So now I have coulombs, and I've got this. There's 96,500 coulombs per mole of electrons transferred. And with iron 2 sulfate, that would be iron 2 plus. So that would mean that this was losing 2 electrons for every mole of iron. And then last but not least, oops, I can get rid of that. Scrunch this down. 1 mole of iron is 55.85 grams. So if I take 25 times 60 times 0.25 divided by 96,500 divided by 2 times 55.85, I end up with 0.11 or 0.109 grams of iron. All right, nuclear chemistry, the smaller the radioactive particle is, the more it can penetrate and the lower the energy. And so the lowest penetrating power is the alpha particle. Okay, the alpha particle is what would be like in a smoke detector or something, while these particles destroy cells. So they have the highest, they can go through the most. All right, and then mass has to be conserved here for these. So I've got 7 and 98, which is going to be 105, right? So I'd have 105 on the bottom, which is going to be dB. And then I've got 15 and 249 is 264, but there's 4 right here, and so that's going to be 260. So this and this equals 264. All right, and then on this one, I'm going to have 274 on the top, but 209 is already right here, so 274 minus 209 is 65. And then I've got 111, but 83 is already used, and so that's 28. And so the element with an atomic number 28 is nickel. All right, I hope this helps. Good luck. Let me know if you have any questions.